Well,
they're pairs, right?
so
Subset of pairwise.
for example, oh, okay. For example, here's an anti-chain, and they're in different ranks. If this were, I mean, this is an anti-chain in this poset. So they don't all have to be of the same rank. An anti-chain is just some subset of the posets such that every two elements of it are incomparable. And so the question asks you to show that even if a Coxeter group is infinite, the anti-chains in it are finite. Okay, so let's get started. We spent the last couple of weeks talking about this beautiful poset on a Coxeter group called the Brewhead Order. And we showed many nice properties of it. And so now what we're going to talk about for the next couple of weeks is a different poset that you can define on the same Coxeter group, on the same Coxeter system. And this 3 really corresponds to chapter 3 in the book. So we're in the Bjorner-Brenty book. So we're going to talk about the weak order and reduced words. Okay. So the weak order is another poset defined on for a Coxeter system. And this poset is going to be very, very useful for us to understand the different ways of writing an element as a reduced word. So this is useful for studying reduced decompositions of an element. Decompositions of the elements of W. So when I say reduced decomposition, I just mean a reduced word for the element. Okay? So let me define the weak order for you. We say that U is less than or equal to V in the weak order, and we denote the weak order by a less than or equal sign with an R underneath. I'll tell you what the R means. If you can write V as U times a bunch of generators, in such a way that each one of these generators makes the word longer. Okay? So we know that when you multiply by a generator, the length either increases by 1 or decreases by 1. And in this case, it has to increase by 1 each time. Okay? So that's what the weak order is. So let's stop for a second and think about the difference between the weak order and the Brewhead order. Okay? Now, one thing I should tell you is that sometimes people, because this one is called the weak order, sometimes the Brewhead order is called the strong order. So if you ever see strong order for a Coxeter group, this is the same thing as the Brewhead order. Okay? And we know that the way that we go up in the Brewhead order is by taking an element and multiplying by a reflection in such a way that you become bigger. Okay? The way that you go up in this poset is by multiplying by a simple reflection, okay, and becoming bigger. So in Brewhead, you go up by multiplying by a reflection. In T, in the weak order, it's almost the same thing, but you go up by multiplying by the simple reflections only. Okay? And this is very important. Multiplying on the right. Okay? And this is the first thing that I would like to point out about this. You should remember that in the Brewhead order, we defined the Brewhead graph by saying that you had an edge from U to UT whenever the length of UT was bigger than the length of U, and T is some reflection. But remember, we talked about this, how this definition looked like the order was important. It looked like it was important to multiply on the right, but we talked about how this is equivalent to allowing yourself to multiply by a reflection on the left. And the reason is that this is the same thing as what? U inverse T prime U. And if T prime is a reflection, then this is also a reflection, because this thing is palindromic, and this thing is the word in one direction, and this thing is the word in the other direction. Okay? So we had these two definitions, and they were equivalent to each other. Yeah? For the Brewhead order, equivalent. Equivalent. But that's not true anymore here. Okay? For the weak order, it is very important that you keep track of what order, of what side you're multiplying on. And it's so much so that actually we have two orders, which are the right weak order and the left weak order. Okay? So for the weak order, it matters to multiply on the right. Okay, so there's such a thing. I mean, a more accurate name for this is the right weak order, because there's also such a thing as the left weak order, where the definition is exactly the same, except you just put, so if you wanted to define the left weak order, then you would just put these S's on the left of U. And this would give you a different poset called the left weak order. But as you can imagine, these posets are basically the same thing. I mean, if you have studied the properties of one, you just rename everything to the left, and you get the properties of the other one. And so when we talk about the weak order, it's customary to talk about the right one, knowing that if you ever need to say anything about the left one, it's the same thing. Okay? So, for example, let's do the weak order for our favorite Coxeter group, S3 with generators S1 and S2. Okay. So what does this look like? Well, again, the bottom element is the identity, and now I can go up by multiplying by generators. Okay, so I can multiply by S1, or I can multiply by S2. Both make me longer, and so they make me go up in the poset. Okay, now what's above S1? Well, to go up, you have to multiply by a generator on the right, which is either S1 or S2. If you multiply by S1, that brings you down, so that's no good. So the only way to go up is to multiply by S2 on the right. And in the same way, the only way to go up starting with S2 is by multiplying by S1 on the right. Now what's above S1, S2? Well, you either multiply by S2 on the right, which brings you down, or by S1, which brings you up. And now is this less than this? It is, because if I multiply this guy by S2 on the right, I get this guy. And so this is the Brewhead order of S3. Okay. Now, what would the left weak order be? It would be the same thing, except that these two guys would be flipped. And so that shows you that these are different posets. Okay? This is the right weak order. Okay? And it's called weak because it's obvious from the definition that basically this guy looks kind of like the Brewhead order, except you remove some relations. Because, for example, in the Brewhead order, you could go from here to here, and in the weak order, you can't. But if U is less than V in the weak order, then it's clear that U is less than or equal to V in the Brewhead order. And that's why people like to refer to this one as the weak one and this one as the strong one.
We take the union of the left and the right weak orders? No sense. We get, in this case, we get back.
So you can study a third poset where you allow yourself to basically take the left order, the left weak order, the right weak order, and take the transitive, take the closure of those two, and that defines another poset, which actually there's an exercise about in the book. And I should tell you, it's a poset that people don't know so much about, and there's actually an open problem about it in the book. So if you're interested in thinking about an open problem for the project, you could think about the union of the left and right Brewhead order, weak orders. Okay. So that's the weak order. Now, let's point out some things about this weak order. Let me leave the definition up so we don't forget. And let's talk about some properties that barely require a proof. I'm just going to say a bunch of nice observations. For example, why do I say that the weak order is useful to study the reduced words of an element of the Coxeter group? For example, what are the reduced words for this element? There's two of them, S1, S2, S1, and S2, S1, S2. And I can think of them as going S1, S2, S1, or S2, S1, S2. And by the way this is defined, I have an edge exactly when I multiply by a generator. And so walking up from the identity to some element is exactly the same thing as writing this element as a product of generators. And so that means that the reduced words for W are exactly the same thing as the maximal chains from let me write it in this way, the maximal chains in the interval from E to W. Now you realize this is dangerous notation because when I give you something like this, you don't know if you should think about it in the weak order and the Brewhead order. And the way we solve that is by putting a subscript here that says we're talking about the right weak order. Okay? So this is clear. And that allows us to study reduced words by studying the poset. Okay? Now the next thing I would like to do is remember that for the Brewhead order, I defined it for you, and then it took us a little bit of work to show these three key properties. So one of them was the subword property, then the chain property, and the lifting property. And so I want to show you analogs of those properties here. So what's the analog of the subword property? Well, it kind of looks like this. Basically, when is U less than or equal to V in the weak order? Well, this is true if and only if there are reduced words that look like this. U looks like this, and V looks like that with other generators appended to the right. Okay. So this is just absolutely obvious from the definition. Take a reduced word for U and complete it to a reduced word for V. So, but you realize that this is exactly the analog of the subword property, which in this case is called the prefix property. Okay. So u is less than or equal to v if and only if I can think of a reduced word for u as a prefix of a reduced word for v. Okay. Okay. What was the chain property? The chain property told us that in the Brewhead order you have levels. And so every chain from level A to level B has exactly B minus A steps in between for any maximal chain. Okay. Well, that's obvious here because how do you go up in the poset? By multiplying by a generator in such a way that the length goes up by 1. So really there's nothing to prove here. So the weak order is also graded by length. And so this is the chain property. We get it for free. Okay. The last one was the lifting property. Okay. What does the lifting property look like here? It looks like this. Let's say that I have a U and a V, and I'm wondering whether they're comparable. Okay? And let's say that I have some generator S that makes them both smaller when I multiply on the left. Okay? So this is kind of the same setup as the lifting lemma for the Brewhead order, but in the lifting lemma, I require to have the relationship that SV was less than or equal to U. I don't require that here. What the lifting lemma says here is that these two guys are either both there or neither one of them is there. Okay. So suppose U is bigger than SU and V is bigger than SV, then you might as well, if you want to compare these two guys, it's the equivalent to comparing these two guys. So U is bigger than V if and only if SU is bigger than SV. Okay. How do you prove this? Well, again, this is pretty obvious because if U is bigger than V, that means that V is a prefix of U. And if you add S's to the left, then SV is a prefix of SU, and vice versa. So again, this comes for free. There's really not very much to say here. And this is the analog of the lifting property. Now you should remember that proving these properties for the Brewhead order took quite a bit of work. We spent a couple of classes doing that. And here, we haven't really worked yet. Just kind of used the definitions. Okay. Now, any questions so far? So far, the weak order is not. It's easier than the Brewhead order so far. Let's prove a more interesting property. So for that, let me remind you of a definition. So given an element of a Coxeter group, we've used this set several times. And this is the set of reflections that make W shorter. And the L refers to which side you're multiplying on. Okay. So these are the reflections such that when I multiply W on the left by T, I get a shorter word. Okay. Now, we know that this is equivalent to TW being less than W in the Brewhead order. Now, remember that if we had a simple description for this, that if we took an expression for W and we took it to be reduced, then we knew exactly what these guys were. They're exactly the ones obtained by starting at the beginning of the word, working your way up the word, and then back down the word. Okay? So we proved that this is basically the set of things of the form S1 up to Sk and down to S1. For one less than or equal to k, less than or equal to n. Okay. Now remember that actually this statement is also true if this is not reduced, and this was basically the exchange lemma, the exchange property. But remember we said that if this word is reduced, then this list is completely irredundant. Okay. And in particular, that means that the number of elements in here, the number of reflections that make W shorter is exactly n, because there's the different possibilities, and n is just the length of W. Okay. So this is just a reminder. Now, the reason that I give you this reminder is the following. We have a very nice description of the weak order. So U is less than or equal to V in the weak order if and only if the reflections that shorten U are contained among the reflections that shorten V. Okay. So this gives me a kind of a set theoretic way of testing whether two things are comparable or not comparable in the Brewhead order. Okay. So let's go ahead and prove this. So let's go first in this direction. Let's assume that U is less than or equal to V. Now, you kind of go there and see, okay, well, how should I think about this? Well, we want to talk about these sets, right? And a nice way of describing these sets explicitly is by working with a reduced word. So to think about these sets, it's useful to think about reduced words. And we know that there's a very good way of thinking about this in terms of reduced words. The way we should think about this is it means that U is a prefix of V. So I can think of U as something like this, and V as something like this. Okay. And then once I think about it in this way, I'm done, because basically I take something in TL of U, but the things in TL of U look like you start up here, you start at S1, you go up to SI, and you go back down to S1, right? For I less than or equal to K. Now you have to justify that this thing is also in TL of V, and the question is, can I obtain this in the same way? And of course I can. I start at S1, I go up to SI, and I come back down to S1. So this is also in TL of V, and I'm done. Okay. So that proves one direction. Now let's prove the other direction. So for the other direction, let's assume that these guys are contained in these guys, okay? And I want to show that U is less than or equal to V. So what I want to do is start by taking a reduced word for U. Okay? And of course, my goal is going to be to show that I can write V starting with U. So I take this thing reduced, and I know what TL of U is. It's S1 up to Si, down to S1 for I between 1 and K. Okay? Now, I have to build a reduced expression for V that starts like this. And the only thing I know is that all of these guys are in TL of V. And so what I'm going to do is build it one step at a time by first proving that I have a reduced expression of V that starts with S1, then showing that I have one that starts with S1, S2, and inductively building up something that starts with S1 up to Sk. So claim sub I is that I can write V as S1 up to Si and then some other S's. I don't know, S1 prime up to Sj prime. So that's claim sub I. And when I prove claim sub K, I'll be done. Okay? And so let's prove claim sub I by induction. So induct on I. So the initial case is claim sub 0, which says I can write V as something that starts with V. Nothing. There's no requirement here. This is free, right? So the initial case is obvious. The key thing is going to be the inductive step. So let's prove that claim sub I implies claim sub I plus 1. Okay. So I have V written in this form. And what I need to show is that I can now cook up a different expression for V, where this is an Si plus 1. Now, you know what I have available to work with. All I know is that all of these guys are in TL of V. Okay. And now you ask yourself, okay, well, how should I use that? Well, what things are in here? S1 is in TL of U. I know that S1 is in TL of V. S1, S2, S1 is in TL of U. I know that S1, S2, S1 is in TL of V. So these aren't useful. So what's the first one that's useful? The first thing of this form, which is not obviously of that form. And which one is that? It's S1 up to Si plus 1, and then down to S1. So that's the one that I'm going to use. So I know that S1 up to Si, Si plus 1, Si up to S1 is in TL of V. This is what I'm going to use. I should have said I can write this in a reduced way, right? I need it to be reduced. And so I'm assuming that this is reduced. So if this is reduced, then I know exactly what's in TL of V, right? It's start here, up and down. And so what I obtain is that this thing must be written as start with S1, then go up to Si, and then continue with some S1 prime, and then let's say that you go up to SA prime, and then you come back. Okay. Which means starting from the beginning of V, going forward, and then going back. Now, why do I have to go past Si to the S primes? The reason is that the ones that I obtain by starting at S1, not crossing to the Si primes and coming back, have already been listed in this set, and we know that all of those guys are different. Yeah? So that's why I have to cross over to the S primes. Okay? So I have a relation that looks like this, and what can I do? Well, it looks like I can basically cancel this with this, cancel this with this, and I have expressed Si plus 1 in terms of these S primes. So that looks promising. So Si plus 1 looks like this. And so let me rewrite this a little bit differently, because what's my goal? Well, it's basically to get Si plus 1 to go in here. Yeah? And so what I'm going to do is take S1 prime up to SA prime, which is over here. And I would like to replace it with Si plus 1, blah, 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 blah. Right? And that's exactly what I am allowed to do here. What is S1 prime up to SA prime? Well, I can solve for it here and obtain that it's equal to Si plus 1, S1 prime up to SA minus 1 prime, and substitute. So V is S1 up to Si, then S1 prime up to SA prime up to Sj prime, and then I'm going to take this piece over here and get rid of it. Well, not exactly get rid of it. What I do is basically just substitute for this, and that just shifts over these guys as A prime disappears. I get something like this. Yeah, so I replaced this with this. Okay. But you see, these two things have exactly the same length. They have length A. Right? And that means that if this expression was reduced, this one has the same length, so it must be reduced. So this is reduced, and it starts with S1 up to Si plus 1. So this proves claim sub I plus 1. And that does it. That finishes my induction. And that proves that U can be thought of as a prefix of V, which shows that U is less than or equal to V in the poset. Okay. So maybe what I would like to do now is talk specifically about the symmetric group. And so two things. First of all, what is this saying about the symmetric group? And second of all, how can I think of this weak order concretely in terms of the symmetric group? So what is this saying for the symmetric group? So what this is saying for the symmetric group is that we have to remind ourselves what these sets look like for the symmetric group, right? So let's do that. Let's say that I take some permutation. U is equal to 3, 8, 1, 5, 2, 4, 7, 6. Okay. So what's TL of U? Well, it's the things that, so first of all, what is T? T is transpositions, right? Not necessarily adjacent. And so what I need to ask myself is, what are the transpositions that make this word longer or shorter? For example, what about transposition, let's say 2, 5? No, 2, 8. Is this longer or shorter? Well, we have to remind ourselves what it is that multiplying by a transposition does when you multiply on the left. You remember? So it switches either the numbers 2 and 8 or the positions 2 and 8. So which one is it? Let's go ahead and do this to be sure. So 1 goes to 3, which doesn't get touched. 2 goes to 8, which goes to 2. 3 goes to 1, doesn't get touched. 4 goes to 5, doesn't get touched. 5 goes to 2, goes to 8. 6 goes to 4, doesn't get touched. So actually switches the numbers 2 and 8. Okay. So does this become bigger or smaller? Which permutation is bigger? This one is bigger than this one, right? Because it's more out of order. Remember that the length is the number of pairs that are out of order. And so TL of U is basically the pairs ij such that the numbers I and j are out of order. So what does this mean? If I would like to check whether these two permutations are comparable, what I do is that I look and see what's out of order here, what's out of order here, and see basically, so the question is every pair out of order? So every pair that is out of order in U, also out of order in V. Okay. That's how you check this here. So that's the first thing. Now, what is it then that I'm doing in the Brewhead order for the symmetric group? How do I walk up? So again, in Sn. So I go from U to U times Si for some I. Okay? So this is how I go up in the weak order. Like this. Now, combinatorially, what am I doing here? What am I doing when I take a permutation like 3, 8, 1, 5, 2, 4, 7, 6, and I multiply it on the right by transposition like, I don't know, 5, 6, which is S5. What does this do? Well, if multiplying on the left switches the numbers to an 8, then that reminds us that multiplying on the right changes the positions to an 8. So when you multiply on the right by 5, 6, what you're doing is looking 1, 2, 3, 4, 5, 6, and you're going to switch these two positions. 3, 8, 1, 5, 4, 2, 7, 6. So how do you walk up in the weak order? Well, basically what you do is you just switch two adjacent things at a time. Okay. Switch adjacent positions and become bigger. Okay. Now, I'm wondering if I'm brave enough to draw the Brewhead order for n equals 4 in front of you guys. Maybe not. Maybe I'll just ask you to look at your book. And if you look at page, what page is it, John?
I believe it's
31. So if you have the book with you, or if someone next to you has it, then look at page 31. Okay. And this is something that you'll see in general, that if you look at the drawing of the Brewhead order, it looks like a polytope. Look at it. It should look to you like the Brewhead order for S4 should look to you like a three-dimensional polytope. If you look at it long enough. No, not Brewhead, weak order. I'm sorry. So that's a different page. Yeah, the Brewhead order, we talked about this last time. Well, actually, we didn't talk about exactly this last time. But if you look, well, I'll let you look it up and tell me what page it is. But the weak order on S4, which is in page 67 of Bjorner and Brenty. If you look at it, it looks like a polytope. Looks like a 3 polytope. Stare at it long enough and you'll see it. So proposition, the weak order on the symmetric group Sn is the skeleton of a polytope. The one skeleton of a n-1 dimensional polytope. So if you're used to staring at polytopes enough, you might recognize that this is a zonotope, if you know what that means. And this is actually true. So let me tell you a little bit about this polytope, maybe in this example. So this proposition should be true here, right? So this should look like the skeleton of a polygon. And it does, and this is already nice enough, because you see the Brewhead order did not look like a polytope. Yeah? This one does. It looks like a hexagon. Now I'm going to tell you exactly what hexagon it is, exactly what polytope it is. This is something called the permutahedron. So what is the permutahedron? Well, first of all, what is a polytope? Well, in the plane, a polytope is a polygon. In 3 dimensions, a polytope is what we're used to thinking of as a polyhedron that is kind of nice and bounded. In general, in more dimensions, a polytope is you can think of it as you decide what the vertices are, and the polytope is the convex hull of those, which you should think of as kind of wrapping a high-dimensional rubber suit around these points, and then it just kind of snaps into place and defines a polytope for you. So the permutahedron pi n is the convex hull of the points. How many vertices does it have? We know that this is supposed to be a skeleton, and so whenever we see a point here, it should correspond to a vertex here. So we should have m factorial vertices. And the n factorial vertices are just going to be the permutations of the numbers from 1 up to n. Okay. So for example, what does this look like? See, this is already a scary picture to draw. What does pi 3 look like? Well, this lives in 3 dimensions. Okay. There's 6 vertices, and they're basically 1, 2, 3, 1, 3, 2, 2, 1, 3, 2, 3, 1, 3, 1, 2, 3, 2, 1. Now you might be worried that I'm looking for a hexagon, and I'm living in 3 dimensions. And the reason you shouldn't worry is that if you look at these 6 points, they're all on the same plane. They're all on the plane x plus y plus z equals 6. Okay? That plane looks like this, something like this. X plus y plus z equals 6. And if you plot these 6 points, they're going to look something like this. And there's your hexagon. So this is true in general. This is going to be one of the homework problems. Just to show this. This is a nice problem, and it's not as hard as you might think it is. And that shows that actually, at least for the symmetric group, the weak order is a beautiful thing. And in general, we're going to see that the weak order is also very nice for any Coxeter group. Batteries, so once a week I have a battery like this that still works. That's what might stop working.